Imagine you are standing at the bottom of a staircase with n steps. You can take either one step or two steps at a time. The challenge is to determine exactly how many distinct ways you can reach the top. For example, if there are 3 steps, you can go 1 1 1, 1 2, or 2 1, giving us 3 distinct ways. This problem might seem simple, but it hides a powerful mathematical pattern. A naive approach would be to use recursion, branching at every step into 2 new paths. This creates a binary tree of calls that grows exponentially with n. You will recalculate the same subproblems over and over again, wasting precious time on redundant work. To fix this, we recognize that the number of ways to reach step n is the sum of the ways to reach step n-1 and step n-2. This is the classic Fibonacci sequence pattern. We can solve this efficiently using dynamic programming with constant space. First, we handle the base cases where n is less than or equal to 2. If there is only one step, there is only one way to climb it. If there are 2 steps, you can take 2 single steps or 1 double step, giving 2 ways. Next, we initialize 2 integer variables to track the previous 2 results. We set one variable to represent the ways to reach step 1, and the other to represent the ways to reach step 2. These act as our starting seeds for the sequence. We then loop from step 3 up to n. In each iteration, we calculate the current step's value by adding the 2 previous values together. This builds the sequence forward without storing the entire history. After calculating the current value, we shift our window forward. The old previous value becomes the new second previous, and the current calculated value becomes the new first previous. This sliding window ensures we always have the correct inputs for the next step. For extremely large values of n, you could use matrix exponentiation to solve this in logarithmic time. However, for typical interview constraints, the linear scan is preferred for its simplicity and readability. The brute force recursion takes exponential time because of the repeated calculations. Our optimized approach runs in linear time since we visit each step exactly once. We use constant space because we only store 2 variables regardless of n. Whenever you see a problem asking for counts or combinations, check if it follows a Fibonacci-like recurrence. By storing just the last 2 results, you can solve these problems efficiently in linear time.